Set the controls for the heart of the sun. It's a dramatic statement familiar from movies and music, but now a new mission really is ready to plunge into the atmosphere of a star. Not just any star, our star, the sun. 60 years in the making, the Parker Solar Probe is primed to reveal the true nature of the heart of our solar system and the source of the solar winds. Weighing just 685 kilograms, the solar probe was launched aboard a ULA Delta IV heavy rocket. Its thrust of 9,700 kilonewtons may seem like overkill, but the Parker probe has to travel faster than anything before. As a matter of fact, it will be the fastest man-made object ever launched.
Parker Solar Probe really is a historic mission. It was first dreamed of in 1958, and it's remained the highest priority mission throughout that period. The reason it hasn't flown is just because it's taken a while for technology to catch up with the dreams that we had for this amazing mission.
Destined for the sun, our star, this probe is the realization of a dream that has been evolving over decades through the talents of hundreds of dedicated people.
After working on this for 10 years, it is really a pleasure to see it kind of actually coming to fruition. To be one small part of this huge engineering team that is making science dreams come true is just amazing. I can't wait to rewrite textbooks and change the way we look at the sun forever. I'm really excited to pass this off to the mission operations team and see all the science data that comes down and just get to enjoy all that Solar Probe brings us.
This is a 60-year journey that people have gone on to make Parker Solar Probe a reality. And to be there at the finish line, that is definitely the coolest thing about my job.
Several questions arise. How did this project get started? Who was behind it? And why is it called the Parker Solar Probe? It's because of this man.
The Parker Solar Probe is the first mission ever to be named after a living person, our own University of Chicago astrophysicist Eugene Parker.
Born 1927 in Houghton, Michigan, Gene Parker gained his PhD from Caltech in 1951. By 1958, he had developed his theory on the supersonic solar winds and predicted the shape of the solar magnetic field in the outer solar system, which now bears his name, the Parker Spiral.
So Gene Parker had graduated in physics and had a hard time actually getting a job. So he was first doing some researching at University of Utah when he was then invited to come to Chicago. He was not sure he was going to make it in the field. When he wrote his paper, it didn't help that the referees were not in agreement with him and didn't really want to publish his work. So he had lots of challenges early on, but he was right. And this is one of the things that first helped him, be the person that we all recognize as this amazing role model to all physicists, but also the power of science being right or wrong due to experiments. So what vindicated him was not just having Chandrasekhar, for example, helped him publish his article, but what really made him who he is in the history of science is the fact that the measurements showed him right.
Eugene Parker has received many accolades over his career, including the National Medal of Science for Physical Science and the title of S. Chandrasekhar Distinguished Service Professor Emeritus at the University of Chicago.
So in 1958, Gene Parker realized that the sun has a magnetic field and it will have a structure around the solar system that will be populated by what we call plasma. So these are hot particles that are flying from the sun all the way to the edge of the solar system. This is what he called the solar wind. So the solar wind is a structure generated by the sun, which basically envelops the whole of our solar system all the way to the edge. And it has been studied all the way to the edge of the solar system with, for example, the Voyager probes, which are now crossing into what's outside of the solar system, which is the furthest that man has ever been, or any man-made machines have ever reached across the solar system.
I laugh about this because I remember how upset some people were. They insisted I made a mathematical error, and I would reply, well, here you are. Here's 5 lines of algebra, and you see I made a mistake. Show me. And it's amazing the number of people that just couldn't let go of the old ideas. They've been working on the spacecraft for several years, and one day the phone rang, and it was a guy that I know said, we're talking about putting your name on the Solar Probe Plus, it was called. And did I object? And I said, no, I feel rather flattered. So he said, okay, that's what we'll do.
While the success of this mission bearing his name will not be known for many years to come, all the effort is sure to be worthwhile. The advances in engineering required to make this mission successful have been far-reaching and at times ingenious. That's because the speeds required to reach the sun are mind-boggling in themselves.
The solar probe will be reaching the closest ever to the sun and moving the fastest and reaching the hottest regions of the solar system. It's so fast that it could go from Chicago to Beijing in less than 1 minute.
There are many enabling technologies. The solar arrays were very important. The autonomy was very important. One of the ones that was obviously also critical is the heat shield, and developing the technology to actually protect the probe at the sun.
The Parker Solar Probe is a technological marvel. The thermal protection system, the heat shield, will be glowing cherry red. The front surface of that will be 2,500 degrees Fahrenheit, while the spacecraft remains 85 degrees, roughly a warm day in Florida. The material sciences just didn't exist in the 60s and 70s, and so the carbon, which came out of frankly the military, looking for lightweight, stiff, strong structures, were the precursors to your tennis rackets and golf clubs, which are now the precursor to the carbon technologies that we have on Parker Solar Probe.
Temperatures so close to a star can reach a phenomenal range. Serious sunscreening is required.
And a sandwich panel is a lot like a honeycomb panel you find in a traditional spacecraft or on airplanes. You have 2 outer face sheets, and then you have a core. In this case, the 2 outer face sheets are carbon-carbon composite, which is a lot like the graphite epoxy you might find in your golf clubs. It's just been superheated. And then the inside is a carbon foam. So the Parker Solar Probe heat shield has a white coating that's on the sun-facing surface of this giant frisbee that's protecting the rest of the spacecraft. And that white coating was specially designed here at the lab in collaboration with RED and the Space Department, as well as the Whiting School at Johns Hopkins proper, to actually work at the sun. This was specifically designed for Solar Probe. And the concept is basically you'd rather be in a white car on a hot day than a black car on a hot day. It's just that it just knocks down the heat that much more. And so it's helping us stay cool at the sun. That titanium truss was also specially designed for Solar Probe. It's actually a really neat piece piece. It's a welded titanium truss that's about 4 feet tall, but it only weighs about 50 pounds. And the key there is we're trying to minimize the conduction between the heat shield and the spacecraft. So you want to have as little stuff there as possible.
The hottest environments in the solar system will be probed by this mission, and it's instruments that will be measuring all the different properties of the solar corona are protected by a shield, a state-of-the-art shield developed by NASA, which would make Captain America very envious. This shield keeps the instruments behind from being cooked every time the probe gets really close to the sun. So the shield made of reinforced carbon is really something that is very recent technology, and only now we can actually get that close to the sun and really verify some of the predictions that Gene Parker has made over his whole lifetime of trying to understand the solar wind.
Earlier iterations of this spacecraft design were predicated on a nuclear power supply. That idea was dropped in favor of solar panels, which brought their own design difficulties so close to the sun.
Parker Solar Probe needs electrical energy to operate. Like any other satellite, or most other satellites, the spacecraft has solar arrays. But unlike other satellites, we have to generate electricity very close to the sun. For every watt of electrical energy we generate, we have to dissipate 13 watts of thermal energy. To do that, we need a cooling system, and we have a cooling system that's much like you'd find in your car. There are 2 water pumps in the system that pump water through the solar arrays and out into radiators. Those radiators radiate the energy to deep space, which is very cold, as opposed to like a car where it would be radiated to air.
When we're at closest approach, the front surface of the heat shield will be at about 2,500 degrees Fahrenheit. The back surface of the heat shield will be about 600 degrees Fahrenheit. But then the spacecraft bus is basically sitting at 85 degrees Fahrenheit. So the shield is actually really keeping everything very cool, and that's most of the stuff is on the heat on the bus.
If you look at the science data, there's a big gap, and that gap is where Solar Probe is going. We're going to fill that gap of scientific knowledge. So it's true exploration. I mean, in that, and we're not following somebody. We're the first spacecraft, first people to go there. So what will be interesting is not the answers to the science questions. What will be interesting is the new questions that Solar Probe forces us to ask. Because one thing we're pretty sure of is that probably have it somewhat wrong. Solar Probe will teach us what's right. And that'll generate many, many more questions and many more missions to come.
NASA's Parker Solar Probe will soon fly closer to the sun than any spacecraft before it, some 4 million miles from the visible surface. But getting that close to the sun requires some fancy orbital mechanics and a dash of brute force. Why is it so hard to get to the sun?
Another reason Parker Solar Probe wasn't launched in the last 60 years is that getting so close to the sun is hard. It takes a huge amount of energy to get to where we want to go. When a satellite lifts off the Earth, it carries the Earth's velocity around the solar system. So the Earth is moving at about 30 kilometers per second around the solar system.
Of all the space missions I've worked on, Parker Solar Probe is the most challenging and complex mission to design and to fly. The launch energy required to reach the sun is 55 times of required to get to the Mars and 2 times to Pluto.
Traveling so close to a star can also affect communications with Earth. In such a dangerous environment, engineers had to design software with serious smarts.
So Parker Solar Probe uses a sophisticated rule-based autonomy system to protect itself. For long periods of time, the spacecraft can't communicate to the Earth, and it needs to take care of itself. So the engineers during the development phase spent a lot of time thinking about what faults could affect Parker Solar Probe and came up with solutions for those faults. Those solutions are encoded in this rule-based autonomy system so that even if there's a fault on orbit, which of course we hope there isn't, the system can take care of itself. One of the most common questions I get are, what happens if the spacecraft gets hit by a solar flare or gets hit by a coronal mass ejection? Will it be destroyed? That's a very common question. And what I tell people is the science community will be elated if we were to get hit by a solar flare or a coronal mass ejection. They're very dramatic events when you look at them in a telescope or during an eclipse. But in the reality, they're very ethereal. The density of the particles isn't so high from the point where it could actually cause damage to the spacecraft. But the instruments aboard the spacecraft, the electromagnetic field instruments, the high-energy particle instruments, the plasma instruments, and the visible white light sensors will see this event. And how dramatic would that be to see a solar flare coming at you and to fly right through it?
The sensor suite on board the Parker Solar Probe is indeed impressive. Each was designed to withstand the harsh radiation and temperatures to measure the particles, electric and magnetic fields of the solar wind. There is also an imaging instrument on the spacecraft called WISPER.
The WISPER instrument is the only imaging instrument on the Parker Solar Probe, and it is looking in the direction that the spacecraft is traveling. And what it sees is light scattered by the dust that's in orbit about the sun. But then, once we remove that, what we see is the light scattered by the electrons in the corona, in the solar wind. These measurements that we're making from the WISPER instrument have been made before by other instruments from 1AU, from the distance of the Earth, about 100 million miles from the sun. By getting closer, we're increasing then the ability to see what's really close to the sun. The fact that you're close means that you don't have all this material that's in between you and the object that you're really interested in. And that contributes to background noise. And so you're looking at something that's much more pristine. You're looking at just that object all by itself.
We have 3 sensors that measure magnetic fields that are mounted on a boom behind the spacecraft in the shadow shield. And then we have 5 sensors that measure plasma voltage. These are electric field sensors. They extend into full sunlight and they get very hot. There are 2 ways to measure electric fields in space. One is using a technique that's called a double probe. And then there's another technique which is measuring plasma waves or radio waves. And Fields for the first time brings these 2 techniques together. I think the very first data that we get will be revolutionary. At first blush, it'll just be a bunch of numbers as a function of time. But the science team, will take those numbers and make visualizations in the form of spectrograms, and eventually those data will be related to models, and so we'll be able to compare directly 3D visual models of the coronal magnetic field. 2 of the key measurements to understanding coronal heating are the measurement of the magnetic field and the electric field, and together they give us what's called the Poynting flux, which is the energy flux of the corona. And to make those measurements, we have to actually go into that plasma and put sensors in the plasma to measure magnetic fields and electric fields directly, and that's what Fields will do. These measurements have never been made in the environment close to the sun. We've made measurements similar to this in the Earth's magnetosphere, Earth's ionosphere, but putting a package like this into the solar corona it's just never been done. The closest anyone's ever been to the sun, and based on what we've seen so far from spacecraft not quite as close, it's going to be striking and I think revolutionary.
The other science packages aboard Parker include SWEEP and ISIS, designed to study the particles emitted in the solar wind.
ISIS, the Integrated Science Investigation of the Sun, is an experiment which looks at energetic particles over a broad range of energies, from tens of thousands of electron volts up to about 100 million electron volts. The ISIS instrument is based on solid-state detectors. Those are detectors that when a particle passes through them, energy is deposited, and you can measure that energy and you can measure that the particle has actually passed through. So there's the solar wind, which is this continuous flow of lower energy particles. And then there are much more sporadic and episodic events like solar flares that spew out great numbers of these much more energetic particles. In our higher energy instrument, we have a whole set of layers of these detectors. And when a particle passes through those layers, it leaves energy in each and every one of those detectors. Those detectors are also segmented in pieces like a pie. And so when a particle comes through from a particular direction, you can tell both the direction the particle came through at, and you can tell the energy and species of that particle.
The SWEEP investigation consists of 3 separate instruments and a central electronics box. Most of the instruments within SWEEP sit on either side of the spacecraft, stare out over the entire sky, and make maps of all the different particles and what energies they're moving at, what types of particles they are. The purpose of SWEEP is to measure the bulk of the solar wind and the solar atmosphere. One of the biggest questions we want to resolve with Solar Probe is how the corona and the solar wind are heated. In order to do that, we need to see if there are waves that are coming from the sun and depositing energy within the solar atmosphere and the solar wind. So we have a series of sensors across the spacecraft that will collect individual particles, electrons, fully ionized hydrogen and helium, which we call protons and alphas, and other minor ions, and make maps of the number of particles as a function of their speed and energy and type. We take those maps on the ground and we can interpret them to figure out the temperature, the density, the pressure of the solar wind and the solar atmosphere.
Learning the secrets of our star, the Sun, will help us understand the nature of the solar system and its all-embracing influence on our world. But the Parker Solar Probe is not the only mission destined for that star. The European Space Agency is also in the game. In collaboration with NASA, the Solar Orbiter is set to launch very soon and will be joining Parker in its quest for knowledge. The orbiter will fly an elliptical orbit within the orbit of Venus, but on a much greater inclination off the ecliptic, giving it access to the poles of the Sun. Unlike the Parker probe, the orbiter's main observation instruments will peer through the solar shield at a safe distance, then reconfigure when making a closer approach. Together, they will reveal the secrets of our closest star, the Sun.